In this module, we will study methods of solution of equilibrium equation. So, the outline of this module is dynamic equilibrium equation we will discuss, and then what methods are available for solving this dynamic equilibrium equation. So, dynamic equilibrium equation we discussed earlier in the earlier module, that is by force approach. So, this is a single degree of freedom system, and then that can be converted into mass spring damper system. So, where force, displacement, stiffness and damping all are represented. So, stiffness is represented as a spring and which is resisting the motion, and damping is represented as a dashpot which is removing the energy in vibration. So, this is stiffness, and if we draw the free body diagram of this system of vibrate body, then external force P acting in the right direction, and then as we discussed earlier, according to D'Alembert's principle, moving mass generates inertia force opposing motion. So, that is why mass is moving in the opposite direction, but inertia force is generated in the reverse direction. So, forward direction and inertia force is generated in the reverse direction. So, that is how it is represented in the back side. When mass is moving in the forward direction, the resisting elements, so which are columns or vertical resisting elements of the building, are trying to pull it back. So, that is represented by elastic force. So, that is equal to stiffness multiplied by displacement, and damping force, which is removing the energy from the vibrating body, that is damping C multiplied by velocity. So, if we write the dynamic equilibrium equation, these three terms, inertia term, damping term and stiffness term, which is all put together equal to externally applied force. So, in structural dynamics, understanding the parameters mass, stiffness and so mass, damping and stiffness is very crucial. So, now how do we solve this dynamic equilibrium equation which we derived just now? So, there are four methods of solving this dynamic equilibrium equation. So, the first one is classic method of solving dynamic equilibrium equation, and the second one is Duhamel's integral solution, and third one is transform method, and fourth one is numerical method. So, we will discuss in brief each method. So, let us discuss about the classical method of solution. So, in this classical method of solution, so what we are going to do is a differential equation. The solution of differential equation will have two components. So, one is called complementary function, that is u complementary, which is a function of time, and then the second one is u particular, which is also a function of time. So, the sum of these two, that is complementary solution and particular integral, will give us a total solution. So, complementary function we can also call it as a free vibration component. So, this depends only on the structure's natural parameters or natural properties of the structure decide this free vibration component. This can also be called as transient motion or transient component of vibration. And then particular integral. So, particular integral up, which is dependent on applied force. So, whatever force we are applying, so that force is taken into consideration while solving this component. This is also called steady state component. So, u complementary, u particular, u complementary transient, u particular is a steady state component. So, the total solution looks like this one. So, complementary solution and particular integral. And the second method is called Duhamel's integral. So, in this Duhamel's integral, so what we do is whatever externally applied force is there, so that is divided into several components. So, in this method, applied force is represented as a sequence of infinitesimally short impulses. So, for example, if applied force is there like this one, okay, as input motion, then this can be divided into small components, and then each component is taken separately and solved, and later all those things can be added by using superposition principle. So, the response is obtained by adding the response to all impulses up to that time. So, this is in the Duhamel's integral. So, a typical equation of Duhamel's integral is this shown here in this one. So, this is a solution of one impulse, and then we are integrating over many impulses. So, this is a total response. So, this is a response due to one impulse, and that is integrated over all the impulses up to that time. So, this is a second method of solving dynamic equilibrium equation. Now, there is a third method. So, the third method is like transforms, either Laplace transform or Fourier transform. So, usually Fourier transforms are used extensively in structural dynamics. So, what we do in this Fourier transform is convert the equation which is differential in nature, that is converted into algebraic equation. So, while converting this differential equation into algebraic equation, so what happens is the equation which is present in the time domain gets converted into frequency domain. So, here like equation is represented on the time scale, amplitudes are represented on the time scale. In this one, amplitudes are represented on the frequency scale. So, u cap of omega. So, in this one what we get is what is the energy or what is the amplitude of vibration at different frequency levels, whereas in the time history analysis, which is coming from the differential equation approach or the classical method, we get time history at each time, and here we get amplitude of vibration at each frequency level, and yeah, this is how we convert. So, this P of t is a force which is the signal in time scale, and P cap of omega is a signal in frequency domain. This is in frequency domain. The fourth method is numerical method. So, this numerical method is mainly used for dealing with the non-linear systems. So, other three methods are applicable only for linear systems where principle of superposition is applicable. Superposition is applicable. So, principle of superposition, what it says is, say for example, if I apply a load of 1 kilonewton and I get some deflection, and later I apply say a load of 2 kilonewton and I get some deflection, and later I apply a load of 3 kilonewton and I get some deflection. Superposition principle says that all these loads put together 1 plus 2 plus 3, if I apply all at a time also, I can get the same principle. So, that is the principle of superposition. So, where principle of superposition is applicable, there we can use a classical method, second Duhamel's integral, and third we can use transforms. Okay, when it comes to nonlinear analysis, the superposition principle cannot be applied. So, we need a more powerful technique for solving dynamic equilibrium equations. So, that we rely on numerical methods. So, all three methods are restricted to linear systems and cannot consider inelastic behavior of the structures during earthquakes. So, if the ground shaking is intense, so we use non-linear methods. So, we have several non-linear methods. So, for example, say we have central difference method or Newmark's method we discuss. And the another advantage of this numerical method is all these other methods, especially classical method, we can use this classical method when we are idealizing the structure into single degree of freedom system, 2 degree of freedom system, 3 degree of freedom system, like that. If number of degrees of freedoms are increasing enormously, so then it is difficult to handle using methods which are described. So, then we need to rely on numerical methods. So, that is the advantage of these numerical methods. And then in summary, what we have discussed in this module, that is methods of solution of dynamic equilibrium equation. So, classical method, Duhamel's integral method, transforms, and numerical method.